We'll do a strain transformation problem. We'll end up calculating some principal strains and also a maximum shear strain. The other thing, we will also draw these elements at principal strain and maximum shear strain. So go ahead and read the problem statement. As you do so, something should jump out. It says that this is a plane strain element. So that would mean that the strain in the z direction is held at 0. It's most likely held by stress in the z direction, but it really doesn't matter how. It's just that the strain in the z direction is equal to 0. So that'll come in when we calculate principal strains and the maximum shear strain value. So take a look at the strain state right here. It's given to you in equation form using equation sign convention. So go ahead and take a shot at drawing those strains on our strain block. So in the x direction, we've got positive strain, which would be elongation. We're going to call it 60. In the y direction, we've got a much bigger one. It's going to be 240. And the shear strain on the x face, it's going to be going in the negative y direction. It's going to have a value of 50. And then I can draw all the rest of the shear stresses because heads and tails must match. So to get onto Mohr's circle, we're just going to plot the strain state on the two faces. So on the x face, I've got a normal strain of 60. I've got a shear strain at a gamma of 50. And again, let's go down to the Mohr's circle. We're going to put normal strain on the horizontal axis. We're going to put shear strain over 2, gamma over 2. Clockwise is positive. So we're going to use plus 50 over 2 because the shear strain on the x face would cause the element to rotate clockwise. So on the y face, we've got positive 240. There is a shear strain that would be causing the element to rotate in the counterclockwise direction. So we're going to use 50 over 2. So the procedure from here is extremely similar to what we do with Mohr's circle for stress. Again, the only difference is that we've got normal strain and shear strain as our axes. So we're just going to plot the x point and the y point and connect them. And so we plot the x point at 60, 25, the y point down at 240, negative 25. And really now we're off and running. We'll be able to find all of our principles, everything, by just finding really two main elements. I need the center and we need the radius. So we'll do it right up here, the center. All I'm going to do is take both horizontal coordinates, add them together, and divide by 2. So 60 plus 240 divided by 2. So we end up with 150. So I'm just going to put that right there. And again, that is epsilon average. To find r, we're going to use Pythagorean theorem. We're going to use a triangle right here. So we've got a height of 25. This goes from 60 all the way to 150. That's going to give me a length of 90. So we've got 90 squared plus 25 squared. Gives us an answer for r squared of, let's give it for r, of 93.4. So we just go back to our picture, and if we were to strike that whole circle, there's a principal strain, there's a principal strain, and there would be an in-plane strain, shear strain. So at the moment, we're going to call this epsilon max. We're going to call this epsilon minimum. So to calculate those, all we need is equal to the center plus r. Again, that's why those are so powerful. 150 plus 93.4, so 243.4 microns. The minimum would be equal to the center minus r, which would be 150 minus 93.4, be 56.6 microns. So let's just kind of redraw this here. So there's our two values. All right, this is a plane strain problem. So I know that epsilon z is equal to 0, which in this case we end up with epsilon 1, epsilon 2, and then epsilon 3 is going to equal 0. So here are our principal strains, all three of them. And we'll point out that we could use these principal strain values to find principal stresses, which we're not asked to do, but we could apply Hooke's law in the 3D sense in the 1, 2, 3 direction, right? The principal directions. So if you kind of scan through these, we've got a sigma 1 over E, and then Poisson's ratio with sigma 2 and sigma 3, whatever those three values end up being. So is be able to solve this by using AX equals B approach. And so the answer for the principal stresses would come from inverting your coefficient matrix. Let's take a look at the maximum shear strain. All right, and that maximum shear strain is always going to be epsilon 1 minus epsilon 3 divided by 2. The max shear strain is the biggest circle. So that's why the determination of the principal strains is very useful here. And the accuracy of that is going to help us out. So epsilon 1 minus epsilon 3 divided by 2 will equal gamma max over 2. All right, this is the diameter of the biggest circle. Epsilon 1 minus epsilon 3. We're going to divide by 2 to get the radius. And gamma max over 2 is where it sits on the Mohr circle. So gamma max is equal to epsilon 1 minus epsilon 3, or 243.4. In plane, we're going to use the biggest circle, right? We would use epsilon 1 minus epsilon 2 divided by 2. So in plane, we would have 186.6. The other one to check would be epsilon 2 minus epsilon 3, which would be a value of 56.6. So we'd be looking for the second biggest circle, right? Would be the, in this case, would be the in-plane maximum shear strain. So we'll go ahead and draw the rotated stress states at theta P and theta S. So this is just kind of a nice review from earlier. So there's our initial strain state. So the procedure is exactly the same. We're just going to end up calculating a couple angles in here. So we've got a pink theta sitting in there. We're going to take, and we're going to end up at the principal by going 2 theta P. We can do that two ways. We can go clockwise or counterclockwise. So this is the clockwise direction. That would be the counterclockwise direction. And we can calculate the pink theta that's sitting inside using the initial triangle. So just like we use the triangle to calculate the radius, right, the r-squared Pythagorean theorem, we're going to use those same two sides, the 25 and 90, to calculate the pink theta. So a couple of theta games will get us to the answer for theta P, and it's all just sitting right in front of us on here. So we're going to do it two directions. 2 theta P plus theta, the pink theta, is going to equal 180 degrees. And that's sitting right on the picture right there. So we can go ahead and solve that, plugging in our numbers, and that gives us the answer in the clockwise direction. Or looking in the counterclockwise direction, we see that the pink theta and 2 theta P are going to be exactly the same. And so we solve and get 7.8 in the counterclockwise direction. So if we go ahead and draw that at theta P, we're going to go in the counterclockwise direction. Right, that means now that the x prime axis is sitting just about 8 degrees above horizontal. And so let's just go back and track what we did here. So we took the x, moved it counterclockwise. It's now sitting in the horizontal axis. So that would be epsilon 2 that would be sitting on the x prime face. So there's the 56.6. Concurrently, the y point is now sitting up there at epsilon 1, which we calculated just a moment ago as 243.4. To find theta s, let's just go right back to some theta games. And so there would be our state of strain. There's the pink theta that we calculated. And what we want to do is take that initial state of strain and we want to rotate it to the up and down orientation. So we're going to take that point and now it's going to be sitting up there. And so our strain state would be oriented in the vertical direction. And so to do that, we would strike through 2 theta s. Or we could take the x point and go in the other direction, and now it will be sitting on the bottom. So we'll explore both of those here in just a second. So there's our initial strains. Gamma over 2 is equal to r, so gamma is equal to 2 times r. So that'll be the value that we put on the rotated strain state. So let's look at our theta games down here. 2 theta s plus the pink theta is going to equal 90 degrees. So that would be that one right there. There's 2 theta s, there's the pink theta, in total of 90 degrees. Go ahead and solve that. We get our answer in the clockwise direction. In the counterclockwise direction, 2 theta s is equal to 90 plus the pink theta. So let's take a closer look right there. There's 2 theta s. I need the pink theta plus 90 more. That'll give me the entire strike. Pink theta plus 90 is 2 theta s. Just plug in and we find our answer for theta s in the opposite direction. And there would be the strain state. We see on all 4 faces we've got epsilon average, and on the faces in the shear strain direction we've got the radius of the circle. It's better to say we have the in-plane shear strain, which we calculated just a moment ago from epsilon 1 minus epsilon 2 divided by 2. And so we can go over the directions of those real quick. So let's go back up here to the x point, which is sitting right here. It now has a positive shear strain. So on the x prime face, which is located in this orientation, right, 37.3 degrees clockwise down, and I'm going to draw on it a shear strain which would cause clockwise rotation, right? Because up on Moore's circle it has a positive number. From that shear strain I can draw all the other 4 shear strains.